Right, hello. Very rough presentation, so excuse. Oh, there's a microphone. Is
that comfortable?
Too short.
Too short? And is that there?
Hello.
So that you need to stay quite that close.
Test.
Yeah, you can hear.
Right. Are you ready? I'm sure everyone's seen the tower on the left. Maybe not everyone's seen the one on the right, which has been built in Texas in 2018 by the VIZIV company, V-I-Z-I-V. And they say they can send power to anywhere in the world, between 93 and 97% efficiency, with data as well. And they've already got a tower being built in Bahrain, so they're going to couple Bahrain with Texas and transmit power. There's 50 patents pending on the system as far as I could tell, and one of the frequencies is about 2 megahertz, but they're not telling very much on how it works. But that's just to give you an idea of what's going on now with this company, which is an angel invested company. So they're either going to do what they say, or there's a lot of unhappy angel investors. This is the, this is a presentation about vortex physics and potential vortices, elementary particles, and the theory of objectivity. And most of the work is from Professor Constant Merl in Germany, in Stuttgart University, I think he is. Now, Professor Merl takes a dualistic approach to the derivation, where he keeps the electric field and the magnetic field as a dual approach, and he uses the Faraday induction and the Maxwell equation, which results into the diffusion equation, and he derives the vortex, which is in the insulation, the eddy currents, which I'm sure you all know the eddy current, which is in the skin effect of the wire. But what he's done is separated the eddy currents from one definition into two. So there's the potential vortex, which is structure forming, and the eddy current, which is chaotic, which you know, noise on the skin of the wire. Right, so these are just a few of the derived equations that he uses. So where is it? So C is proportional to the distance. The electric field is proportional to 1 over r, and the displacement is 1 over r squared, which you'll know from Coulomb's law. And the same for the magnetic field, which is maintaining the duality. You have the permeability and the permittivity are 1 over r, and the conductivity is also 1 over r. Now, there are different types of vortex, and I'll give a couple of pictures of them to show later. So the speed of light, there's two types of the longitudinal vortex time. The scalar waves, as they call, which is what they're using to send the power, probably. And the electric one has the electric field in the direction of travel, and the magnetic one has the magnetic field in the direction of travel. Now, the definition, where the speed of light comes from, is the speed of the ring of the vortex. All the vortexes have the speed of is the speed of light on the outside, on the exterior, is always at c, and the middle is 0. And the strongest field intensity is in the middle, which makes the speed of light 0 because it's proportional to the field intensity. That's the derivation with the duality approach. Okay. Next one. Okay, there's more derivation. So there's the world equation, as he calls it. There's the electromagnetic wave, which you know is a transverse wave. There's the eddy current, which I was trying to explain, is separated from the potential vortex there. They've both got decay constants, tau 1 and tau 2. So that's quite important for defining the structure of matter. And one, of course, is always in the conductor and one is always in the insulator. They're separate, but they meet at the middle. The duality, part of the duality is the skin effect spills over into the insulation. It doesn't just stop abruptly at the insulation, at the skin, which is how Maxwell does his equation. There's another derivation. There's the plasma wave, which I put on because I know we talk about plasma waves here. I'll skip over the derivation. Now what you can do is you can derive the time-dependent and the time-independent Schrödinger equation, and these are back to the time constants T1, tau 1 and tau 2, and you can, as far as I know, the Schrödinger equation has only been observed, but what Professor Merle does is he derives it for hydrogen. Now the interesting thing is that he gets more. He gets this, the normal hydrogen is the special case where I think he sets to tau 2 is 0, but you can have the extended derivation for hydrogen, and some of these will not be familiar if you know the hydrogen wave equation and you know what the layout of the electrons are. This is how the vortices look. So that one is three vortices. So this might explain the when Dr. Michael Claridge talked about the spectrum that he saw, that he didn't know where it came from. Well, you can derive some of the new spectrum by looking at the extended Schrödinger equation. Go for gravity one. The standard way of looking at the losses in a capacitor results in an inaccurate result for how much power loss. But when you do the vortex method, it's almost exactly on with the red and the blue lines. Capacitors also can form a very tiny vortex ring in the middle of the plate, which is not arcing, but it will slowly form over time. This experiment that can be reproduced, and this is meant to be proof of vortex formation. I'll go over the gravity one. Right, the next. Okay. Now the theory of objectivity is C is variable. You know with relativity that C is constant, and with Galileo C is infinite, just to give you an idea of part of the... Boscovich was meant to have been the original person that came up with the equivalent of the theory of objectivity. Okay. These are the derivations for gravity, electric gravity field equations, and you can see that I talked about with with tau, the time constants there, which are dependent on the permittivity, conductivity, permeability. You've got the cross products of Q and E and the magnetic flux there. And this is, he says that this is the start of formulating the physics and the maths to electrogravity, as he says there. And there were no postulates in that, as far as I could tell. He's just derived it. Okay, right. Now the last part. Right, there's only two elementary particles or field vortices is the more accurate way with this. There's the electron and the positron, and he builds all of matter just from the two spherical vortices. One is the plus on the outside and minus in the middle, and the positron is of course opposite. There is the proton, the shape of the proton, so you can see that it's two positrons and one electron on the outside. Now, of course, it's deformed as well because the charge is stronger at certain points, but the magnetic moment is derived exactly as the magnetic moment should be for a proton. And also you'll notice that there's three vortices, which reminded me of quarks, because they say that there's three quarks in the proton. So it adds up to the models, you know, the more standard models. Now there's the proton. There's the neutron. That's looking at it from the top, I think, is it? From the side. Right, so you've got 1, 2, 3, 4 vortices, haven't you? Okay. Now the standard, when they measure the Coulomb force in the standard with the muon, and this can be done for the proton, the orthodox calculation is it comes out predicted as a different amount to what they measure it at. But if you calculate it with the Vortex method, which is the positron, the electron, the positron, the electron in it, and the field strengths are stronger in the middle, and you can add them up as thirds. It works out exactly as this potential gradient. So it explains that the mainstream doesn't. Now, someone mentioned the photon. It's not a very good copy, but someone mentioned the photon before, and how he explains it is it's a positron and an electron constantly oscillating between each other, and possibly the reason why it's not affected by gravity is because the positron, of course, has the opposite charge to the electron, and you know it might be the antimatter sort of equivalent, anti-gravity equivalent of the matter version, unless you go into a very strong magnetic field with a photon, and then an electron and positron just seem to appear from nowhere, which he uses as experimental proof that really there's a virtual electron-positron oscillating all the time in the ether, and could be defined as part of the ether, and it's just the wave that forms it on top. To give you an idea with some of the more complex particle, the elementary particles that CERN keep discovering, you can work them out with the vortex rules, and you can actually work out all the shapes. Now, typically the spin will be they'll add up, but it will be the outside spin that is the one that is of note, and that vortex must rotate in the same direction as that one. When they're together, when they're touching together, they can't counter-rotate. They will be they'll kind of be grating against each other, but they have to be sort of smoothly operating. Now I know the SAM structured atom model, that it was a static model, and this is quite the opposite actually, because everything's in motion and everything's moving, and typically when something's disturbed about it, the light speed c will be converted into the motion, the point vector as c, so it will maintain momentum, and it helps to explain why momentum is maintained because of the rotation. Now there's two electrons very close together, and it's to show, and I think this is quite similar to some of the electric universe with deformed electrons, and it makes for a stronger field in at certain points. But of course with this model there's the plus charge in the middle. Typically the electron is just is a minus charge, and this is a different take as well on it. There's some of the calculation rules for the potential vortexes. Now, an interesting point with it is there's no quantum mechanics for this, for start off, and localization means when the spherical vortex has speed of light of 0 in the center, which is like a ball that's not moving, and now because it has a center where the speed of light is 0, that localizes the particle. Now, for example, the neutrino, which I've not got on the slides, is it doesn't have any center, so it doesn't have any localization. But when the particle, the wave, the field vortex has localization, it will become what everybody calls a particle. But in Professor Mill's model, it's just another form of the vortex. And if you remove the center in some way, then it will become mobile again. I think that's how he. Now you can. There's a lot of predictions with this. The fermions, they always have either 1, 3, or 5 vortices, and they spin at half. And the bosons always have an even number of elementary vortices of 2, 4, and 6, and they will have spins of 1, 2, and 3. And it will follow, all of them will follow that rules, and when you follow rules like that, you can build the other baryons, which I don't have the pictures of. There's an extensive table of about 20 baryons where you can make them up, and you can predict what the next one is that they're going to discover just by following the vortex rules, really, which is what grabbed me with this, because it looks such a powerful thing to do, and especially as there's no quantum mechanics really anyway. I think it's maybe it actually. You're welcome to ask any questions if I can answer them. There's a few others I never put on, which is part of the gravity equation there, which they couple by circular vortices around. I maybe didn't mention before with the experiment I've got set up in the barn. It generates a longitudinal wave, which is coupled between two coils at resonance, and I forgot to put it on this, but the three points to the resonance, and this is the same as scalar wave biology, is that the cells have to be the same frequency, the same wave shape, and out of phase. and the outer phase, I think, sets up the coupling, because if you had two north poles of a magnet, they'd be pushing against each other. They wouldn't form a field line between them. But if you have a plus and the minus, the north and the south pole of a magnet, you would form a strong field line between them. The three requisites for planetary resonance and for cellular resonance are the same wave shape, the frequency and the outer phase. So it's something to look for. I think they mentioned the Birkeland current, and this all ties in, the vortices all tie in with the Birkeland current. I think one of the presentations mentioned that it was out of phase, which was really interesting to me. I can't remember who said it, and they said that there was four now that are out of phase from the sun, and I'd never heard this before. But what that showed to me was that if they're out of phase, it means that the energy from the sun, that the sun is not tuned to the earth properly anymore. And if you look for the phase shift or out of phase, then it would be one of the first signs of less energy coming to the earth through a sort of coupling between the two objects in resonance. I didn't show it on here, but if you work out the vortex of the moon, I'll put it on. The vortex of the moon works out. If you have a speed of light around the moon, and the wavelength of the moon is the circumference, which is about 10,600 kilometers. If you work out the frequency, I think it's about 27.4. Now the Schumann frequency is 27.3. If you include the mountains on the moon, you're probably exactly on the same frequency. So I thought it's quite an unlikely coincidence. It's pretty much exactly one of the Schumann frequencies. I haven't actually worked out the frequency of Saturn's rings, and if there's any connection with its moon. But if there is, it might lock it into like a gravitational orbit. It'll be in resonance with it. If it's not, then you could class it as being unstable. Possibly you could look for, if the moon, I heard the moon's moving away from us at a faster and faster rate. If you look for a frequency shift in the Schumann frequency, you might notice it changing a little bit, which would more confirm if there is a correlation with that. It could explain other things with the moon, like the full moon. You don't get a laser bounce off the mirror on a full moon either. It's only on the full moon. Now, in Professor Merle's field theory, you can explain why the light doesn't bounce off the retroreflectors on the moon during the full moon, because the field strength is stronger, and it can do something to the light where they don't get the big green laser come back to the earth. It's only lasts for about a day or so, I think, and they've never been able to explain it before, why that happens. It's sort of like a type of spherical aberration, but not like the gravitational bending that they have us try and believe on the mainstream media. But yeah, that's it. Hard questions, easy questions.
I got an easy one.
Go for it.
The classic shape of vortex in water is like the trumpet shape, funnel shape.
Yes.
Is that a feature that we see in the vortex that you ascribe to electrical?
Most definitely, yeah. Above the poles it would be, and the sun as well. You would expect to see it over the sun. If you could look down on the sun, it would be a particularly strong one, actually. Yeah, although by definition you can't, it's hard to see. If it's a perfect vortex, like I've been showing in the experiment, although it's far from a perfect experiment, but the more the vortex forms, it can be argued that the more invisible it becomes. But the more stable and long-lasting because they kind of have a kind of permanence to them, especially if they're in the vacuum. And if you've got another vortex, which is the same frequency and wave shape, and tuned to it, they form like a tunnel between the two, and the longitudinal wave will go through the tunnel, and people have measured it in labs at above light speed as well. And the way it's argued is the tunnel shields the background field, the cosmic ray, the cosmic field, or the ether. It shields it inside a tube between the two objects, and that's why the information can go quicker. But there is a thing with the longitudinal wave that you're pulling on the other end, and you're always connected to them instantly anyway. But you know, maybe you have to be outside of the cosmic field as well for that to act quicker. There's a lot of similarities with gravitational waves with Mills and with the scalar waves. Actually, they act. They can act simultaneously. They can both act instantly, but possibly not the same way, exactly the same way. But they're in the same area, I think. And yeah, there are such things as scalar wave detectors as well. And I was asking Wolf Arnold before about gravity detectors, and you can build these things, and they're little coils inside Faraday cages with magnets, and you're meant to be able to detect the scalar waves. Long answer. Any more? Go on, catch me out.
Well, Jonathan, shall we sort of wrap it up there?
One from Eugene, go on.
Quick
Well, I
one.
have 3 questions, but they're going to be short. Can you please return to the picture with the structure of neutron, where you show the charge distribution? Well, yeah, let's use this one. So, my first question is if I understand correctly, the charge distribution is not spherically symmetric here. Is that right?
Right. Yeah, it's a good question, isn't it? Because it's on one side, isn't it?
Yeah, but we know from, at least from deep inelastic scattering experiments where we bombard neutrons with electrons, that it should be spherically symmetric.
Well, it'd still have a moment, wouldn't it, where it would spin around. Why is it on one side?
Yeah, I mean, that graph actually looks okay if you interpret it as a radius and set the origin at the left side. So neutron indeed, or maybe I'm wrong actually, I don't know. So yeah, basically, it should be spherically symmetric, that's what I'm saying.
Right, let me come back to you on that one.
Alright,
okay.
But I have 2 more.
Yeah, it's a good question. I thought you might have some good questions.
Yeah, so
go for it, go on.
Another question is, are those particles, according to this theory, do they have like a definite boundary, or they kind of...
I can answer that one. Yes, they do. On the skin of the vortex, on the edge of it, exactly there yeah, basically.
So this falling off, is it exponential or?
Here.
Yes.
I thought you meant the interaction with other particles. Actually, there's still going to be the force, isn't there? Slowly tapers off.
Okay. So in some sense there is no clear boundary, right? For
no, not for the Coulomb force. No, okay. no. It's the same as before. It's just worked a little bit differently. I didn't say before. Actually, there's no strong nuclear force in this at all. You don't need it. The calculation is it works out, and the weak nuclear force is it uses a neutrino as a justification for the weak nuclear force, and there's a vortex diagram of the neutrino. So again, the only force you've got is the Coulomb electrostatic force, and, you know, of it. Did you have another one?
Yes. So it's a question that I've been asking Ido and James for more than half a year already.
Oh.
And I'll ask it here because it's applicable. So you're saying that neutron is electron and proton.
Yes.
But how do you deal with magnetic moment of electron? It's 3 orders of magnitude more than a magnetic moment of neutron. So how do you get rid of that?
It's the magnetic moments are only from the positron and the electron. You're asking about the proton. Right. Okay. I know. You work out. There's a field. There's a length contraction inside the vortex. So the electric field is proportional to 1 over r inside, basically. Okay. Now this changes the magnetic moment. You can work the magnetic moment out as the 2.76 with a varying electric field. Does that answer that?
Well, not quite.
Not quite.
But okay, I mean.
It's not a problem with the calculation. You just add them up, but they're not all whole numbers because there's a mass variance inside. They're not all the same. They're not the same mass when they're closer to the field. The mass will change. That's why I don't think I put 1 over m squared for the mass variance on that. There's one more formula actually that needs it, and when you've got that, you can work it out. Basically, it's still lost, but yeah. I don't quite get it all, Eugene, but I just try and I kind of halfway there with it. Trying with it. Anyone else? Is that it?
Pierce is in here.
Yeah.
Pierce.